All right, so the next thing I want to talk to you all about is another one of our statistical mechanical ensembles. The first one that I want to talk to you about is the Grand Canonical Ensemble. Now, previously we saw that the canonical ensemble had cells with constant N, V, and T, where heat was allowed to transfer in between the cells, but we had no mass transfer and no heat was lost to the surroundings. So again, in the canonical, we have NVT cells that are inside of our isolated system. Now, while this offers a powerful tool for calculating macroscopic properties, it is limited to fixed particle systems. Notice that each of these boxes has a specific number of fixed particles in each of those little cells for our microstates. If we want to study systems that involve mass transfer, that allow particles to move from one to the other, then N, our number of particles, cannot be constant within the individual cells. For this new proposed ensemble, we must be at equilibrium with respect to heat and matter. So, thus, each of our cells must now be grouped into fixed volume, temperature, and chemical potential. This ensemble is referred to as the Grand Canonical Ensemble, where inside of our isolated system, our cells or our microstates are built up of little groups of constant volume, temperature, and chemical potential. So, molecules can move in between the individual cells, as long as we maintain the same chemical potential, temperature, and volume. Since N can change between the cells, there may be many different energy values within a given group of N particles. Since different arrangements or compositions of N particles can have a different chemical potential or energy, then we need to first specify our number of particles. Then we need to specify J, which is the quantized energy state that we are in. Thus, for each N, we're going to have a specific set of energy states for energy in terms of N and the state that we're looking at. Similarly, we will have a set of occupations for each of our V, T, mu cells or elements within our ensemble. In other words, we're going to have a set of occupations that depend on N and J, or the occupation of a particular combination of N and J. So to get the total occupations, we must now loop over all of the number of particles as well as the states within each of our groups of particles. Therefore, our A, our overall occupation number, now depends on both N and J, and we must loop over both N and J for our occupations. The word occupation here can be a little bit misleading. If we think carefully, though, we see that our overall number of occupations is really the number of systems in the ensemble. The total number of molecules, however, is actually the sum of N systems with occupations A and J. So that means that if I take my A and J, my occupations for a particular arrangement of particles in a particular group of energy values, or for a specific energy, and I multiply that times the number of particles and loop over N and J, then I will get my total number of particles, which is denoted with the script N. As before, if we want the total ensemble energy, I'm going to take my occupations and multiply it by my energies. And in this case, I'm looping over N and J again, looping over all of my occupation, or looping over all of my number of particles within a group and the specific energy of that group. Just like the canonical ensemble, we will also want to maximize our weighting function, omega, which depends on the number of states, as this will allow us to calculate the average for large numbers, average properties for large numbers of systems. For the Grand Canonical Ensemble, we are going to again look at the omega in terms of the states, and since our states are based on, our occupations, and since our occupations depend on both N and J, then we will have our occupations factorial, our total occupations factorial, divided by the product over not only N, but also the product over J, which would be our number of ways to arrange them. Remember, it's our total occupations factorial divided by the bins that each of them fit into, okay? Now, like the canonical ensemble, we will maximize the ln of omega, since we're dealing with factorials, taking the ln of that is going to be easier to work with. And we're also going to use the original two constraints, where we had the constraints over our occupations sum, as well as the energy sum. Here, however, we're going to add a third constraint, which is our sum over our total number of particles, which was big script N. Now, recall that the natural log of omega, if we use Stirling's approximation, gave us big A ln of big A minus big A. Then for our second one, we had minus the sum over A ln of A plus the sum of A. Well, in this case, okay, our sums are going to be looped over again the N and the J. So when we sum over N and J for our little A and J, that will be equal to a positive big A, okay, for our total number of occupations. We have a minus big A plus a big A. So the only two terms that survive are the capital A ln of capital A minus the sum over Nj of A sub Nj ln of A sub Nj. Next, we can evaluate that into our Lagrangian. Remember, the Lagrangian would allow us to maximize a particular function given a set of constraints. Now, since we have three constraints, I'm going to have an alpha, a beta, and a gamma for my Lagrangian coefficients. And I'm going to be taking the derivative with respect to A that depends on both M and J. All right, so evaluating my function, I have A sub ln of A, A ln of A minus my sum over A ln of A and J's minus, and then this is my first constraint, so this is my coefficient, which is alpha prime, times the sum over Nj of A sub Nj minus A, because again, we're setting our constraint equal to 0. Then my second constraint, so I've got minus beta. My second constraint was the sum over Nj of A sub Nj, E sub Nj minus my total energy. And then my third constraint was minus gamma times my third constraint, which was the sum over Nj, A sub Nj times N minus my total number of particles, which was my script N. After a little bit of work, we end up with the partial derivative of my Lagrangian with respect to A sub Mj is equal to negative ln of A sub Mj minus 1 minus A prime minus beta EMJ, EMI minus gamma M. We set that equal to 0. And one thing that I want to point out is that if I group these together, that is my alpha. So then solving, or I should say before I go into that, here when I take the derivative of A sub Mi, that's going to be the mth and ith occupation that maximizes my Lagrangian. So solving for the A sub Mi max, which is denoted with the star, we get A sub Mi star, which is equal to the exponential of negative alpha times the exponential of negative beta EMI times the exponential of negative gamma M. Now notice that we got M and I in here because we're pulling out the mth and ith values within our sums. Now, this will be used, this A sub Mi star will be used to calculate our probability.